XY chart. So off to the side, make sure you can see all this in here. So off to the side, it's really up to you how you want to do this. Our point is r comma theta. So your first thought might be to do r theta. That would make sense. However, the weird thing about doing it that way is the theta is actually your input. If we look here, we actually want to be plugging in for theta and then spitting out a value. I've done it each way over the course of the year. It's really sort of up to you. I usually kind of throw it out there. Because if you do r theta, this makes sense in terms of this point, but you're going to be getting these values first, and your outputs are actually the left-hand side, all right? If we want to flip it so that the theta is your input, that's typically how we do an XY chart anyway, and then your R, just make sure you understand how to graph it. It doesn't necessarily matter to me. I personally think this is a little bit easier, but it's not really a big deal. So it's up to you, okay? But to get these started, this is how we're going to kind of go about doing this, is with an R theta chart or a theta R chart, either way. So we're going to start at 0. So if we just pick that angle 0 right there, and it's just old school, take your theta, plug it in. So if I did R equals 1 plus the cosine of 0, cosine of 0 is 1, and then 1 plus 1 is a 2. If you remember when we plotted these, then you're going to look over here at angle 0, and then we go out 2 steps. So now I have the circles to indicate those number of steps, so that's going to end up being our first point. When we go through these, we don't need to do every single value. We want to be somewhat efficient with this because these could take a while. They're going to be kind of tedious anyway. So what I'm going to have you do for sure, you're going to do pi over 4, and then you want to pick either pi over 3 or pi over 6, whichever one is going to be the easier value. What I mean by easier is, since we're going to be doing the cosine of it, one of them has a cosine value of root 3 over 2. The other one's going to have a cosine value of 1/2. Pick the one that gives you the 1/2, all right? Because typically this is going to get done without a calculator. So in terms of the cosine of pi over 6, that's a root 3 over 2. So we're going to skip this one for right now. We're going to go to the pi over 4. And then we're going to do pi over 3 as well, because that's the one whose cosine is a 1/2. It'll give us a nice number. So for the pi over 4, what we end up with is 1 plus a root 2 over 2. Typically, you would be given this value. Root 2 over 2 is about 0.7. So what this is about 1.7-ish. So if we look at pi over 4, go out a little bit more than 1.5. So we're right around here. And then that's our next point. The pi over 3, the whole reason we picked pi over 3 is so that we knew the cosine value of pi over 3 is the 1/2. So we know this is just 1 plus 1/2, so this is 1.5. So at that, you're going to go out to about 1.5. And then our last one that you're going to do, at least initially, this is not the last one, I shouldn't say that, give you false hope, is if you do pi over 2, come up here, so let x be the pi over 2. The cosine of pi over 2 is 0, plus a 1 is a 1. When we connect them in order, so this is our first point, our second point, our third point, and our fourth point, that's the beginnings of this graph. But as you notice, that's only one quadrant, so we've got a whole lot more to graph in here. So we're going to go to our second quadrant. So this will be a really good review of your unit circle, if nothing else, after a long break and not having to deal with unit circle too much. This has to be a pi over 3 angle here, this one. And in the second quadrant, your pi over 3 angle is 2 pi over 3. So that's the next input value. So if I now do the cosine of 2 pi over 3, we know that's a 1/2, that's why we're picking it. And in the second quadrant, it should be negative. The x-coordinate should be a negative 1/2. So this has a value of 1/2. So at that angle, just go out halfway to the first circle. That's our next point. If we do the fourth quadrant pi over 4 angle, that's 3 pi over 4. So that's our next one. All this. That's our root 2 over 2 again, which is about a 0.7. But in the second quadrant, it should be a negative 0.7. So 1 plus that negative 0.7 is about 0.3-ish. It's really tight in there. And then we're going to skip the pi over 6 angle, and then we're going to go to pi. Cosine of pi is 0. I'm sorry, no, it isn't. -1. And then the 1 plus the -1 should give us a 0. So that means while we're looking at pi, somebody do something in there? While we're looking at pi, when we have a radius of 0, that means we don't go anywhere. So now just connect these. And normally the first one I have is we go all the way through this. We usually have a full 49 minutes. We don't have that today. So we're going to jump to this right here. And I'll just give it away. Not that big of a secret, not that big of a deal. But we have symmetries with these. When we look at the cosine, so if we're dealing with a only cosine polar graph, what you want to understand is we are symmetric to the x-axis. And the reason we want to know that is that it cuts our work in half, because otherwise we're going to have to do all the third quadrant angles down here, all the fourth quadrant angles down here to get this graph. But if we understand symmetry, and I'm symmetric to the x-axis right here, then as long as I know everything above the x-axis, if I just do a reflection around the x-axis, that should give me the rest of this graph. So this has to go through 0, -1, and just do your best to do a reflection right here. And then that is our graph. This is a good old-fashioned, I don't know if you talk about these, I know you do polar a little bit. It's what we call a cardioid. If you look at that, it very much looks like a heart. So it's called basically a cardioid for that reason, because of what it kind of emulates and what it looks like. Okay. One of the things I want you to be aware of, we'll hopefully get to this today. You don't necessarily need to draw these in right now. It won't necessarily apply to this problem, but notice how we have a few horizontal tangents. It's a really common question with these, but what's even more common, and we'll hopefully get to this today, it's the very last question in the notes. Notice how at this point right here, don't we have a vertical tangent? At this point right here, you have a vertical tangent. At this point right here, you have a vertical tangent. At this point here, you have either a vertical tangent or a sharp corner, kind of depending on how everything plays out. So there's a lot of different places where, if you remember, if we have a vertical tangent, remember how we would talk about our derivative is undefined? Really common question with these, because in this case, there's a lot of places where your derivative is going to end up being undefined. All right. And hopefully we get to that problem today. If not, we'll get to it tomorrow. So it doesn't necessarily need to be something you need to put on this graph, but something we want to see when we do these. So when we get to that next one, then notice how this is now a sine. So if the cosine is symmetric to the x-axis, then you guys are all pretty bright people. That would probably mean that a sine curve is going to have symmetry to the y-axis. And the reason that's important, what that then just means, if I could just graph in the right-hand side here, everything on the right-hand side, then we just reflect that around the y-axis and we get the other half without having to go through the entire unit circle to come up with this, okay? So that kind of guides us in terms of how we're going to set up our theta chart. All right, so let me try to section this off a little bit. There we go. So how did I do it the first? Now I don't even know which way I did it. Thetas and R's, okay. So we definitely want the first quadrant. Let me shade it in here. We want the first quadrant. We want the fourth quadrant. Once we have that, we just reflect it around the y-axis. So we definitely want 0. So 1 minus the sine, our input in this case is the 0. Sine of 0 is 0. So 1 minus 0 is 1. So looking at that angle, go out one step. Again, we only need to do one or the other. We don't need to do all of these if we're just kind of sketching this out. Now it's the pi over 6 value that we would want to use, because the sine of pi over 6 is the one that's going to give you the half. So that when we look at this angle pi over 6, which is the first one here, we only go out a half step. So we should just be right there. When we go to the pi over 4, we get that 0.7. So this is pi over 4. The y coordinate is √2 over 2. Again, just estimate that to be about a 0.7. We don't have a calculator in our hand. And 1 minus 0.7 is about 0.3. So right about here. And then finally, pi over 2 will complete the first quadrant. So the sine of pi over 2 is 1. You would end up then with 1 minus a 1. That's our 0, so that one's at the origin. So now connect those. And the reason we want to understand our symmetry, it makes no sense for us to go into the second quadrant, because all you're going to do is produce the reflected version of this around the y-axis. So if we now just do a quick little reflection here, that's our second quadrant part of the graph. All right. It looks like some eyebrows there. Now I look at this on my screen. All right. And then we need the fourth quadrant. So then we want to do with the fourth quadrant. Up to you how you want to handle this. You can certainly call this, we definitely want our pi over 6 angles because of the 1/2 values that they're going to spit out. If you want to call this 11 pi over 6, totally fine. You could also just as easily do a negative pi over 6, and you can kind of reference the fact that we've already done pi over 6, but just account for that with, you know, the correct sign based upon what quadrant you're in. I like going the negative angles, but you don't necessarily have to. It's really up to you. So if we let this be a negative pi over 6, we know the sine of any pi over 6 angle is this half right here that we already would have gotten. But since we're in the fourth quadrant, our y should be negative. So this should be a negative 1/2. So then we would go in that direction out to, that's too far, 1.5. The negative pi over 4, same thing. We already know what pi over 4 is because we did it earlier in this problem. We know that's our 0.7, but since we're in the fourth quadrant, it should be a negative. So negative, or a positive 1.7-ish. And then skip the pi over 3 angle down here. We're not worried about that. It's not necessary. And either 3 pi over 2 or a negative pi over 2. So negative pi over 2. The y coordinate at negative pi over 2 is a negative 1. So we get 1 minus a negative 1, which is a positive 2. Connect those now. Reflect that then. Take this fourth quadrant stuff, reflect it around the y-axis. It's not a great reflection. Let me try that again. That's a little better. And then for sure, another cardioid. Now it's actually vertical. This should very much look like a cardioid, like a heart. Okay. So cosines, we want to be symmetric to the x-axis. Sine symmetric to the y-axis. That will guide you in terms of being able to figure out what these look like. Okay. All right. Now the next one in particular is one of the ones we'll probably deal with the most in terms of questions that will ask this or deal with this. So what we want to identify, cosine, symmetric to the x-axis. So because it's symmetric to the x-axis, what we want is everything in the first and second quadrant. So once we have that, then we're just going to flip it around the x-axis, and then that should be our overall shape. So because of that, when we go to set up, confusing, did I do thetas right? Yeah, thetas and then r's. We want to pick 0 for sure. And then the cosine that's going to give us the 1/2 is the pi over 3 angle. And then we'll do pi over 4 and then do pi over 2. And whatever that gives us, we just flip around the x-axis. That'll also give us our fourth quadrant. All right, so let's take our 0. And we would get r to equal 1 plus 2 times the cosine of 0. So cosine of 0 is 1. 2 times 1 is 2. Add that additional 1. We should be out there at 3. We're going to skip the pi over 6. We don't want to deal with that root 3 over 2. So we're going to go to pi over 4. That's our root 2 over 2. So you would have 1 plus 2 times root 2 over 2. These will cancel. So what we end up with in this case is 1 plus, and then a root 2. If 0.7 is root 2 over 2 divided by 2, then if we're not dividing by 2, we're just doubling the root 2. So that, or the 0.7 to get root 2, and that should be 1.4. All right. Typically, this is a calculator, non-calculator quiz and test, and I would give you these. So go to pi over 4 and go out to about 2.5. All right, and then our pi over 3, we should know. That's why we're picking it, because we know that should spit out a 1/2. So plug in pi over 3. The cosine of pi over 3 is 1/2. The 2's will cancel, so that we really just end up with a 1 and a 1, which is 2. So pi over 3, we go out to 2. And then the last angle to finish off the first quadrant would be pi. What's that? Oh yeah, good call there. Thank you, Brian. Yeah, thank you. So cosine of pi over 2 is, the pi over 2 is going to finish off our first quadrant. And then that is what, 0. So this is just 1 plus a 0. So at pi over 2, we don't go anywhere. So connect those in that order, like that. No, what am I doing? Yeah. No. Try that again here. It's a 1, right? What am I doing? Yeah. Somebody looking at me like I was crazy, so it kind of tipped me off. They screwed something up. And then the graph looked weird. So it should look like this. All right. That then gives us the bottom half, right? Because now we know we're symmetric to the x-axis. So let's go ahead and kind of sketch in what that's going to look like. Rough sketch. Like this. So far it looks pretty similar to number 1. Then things are going to get a little weird. So let's come over here, do 2 pi over 3, because we want to go into the second quadrant. So plug in your 2 pi over 3. We know the pi over 3's over there give us the 1/2. That's why we picked it in the first place. In this case, though, in the second quadrant, our x's are negative. And what you're going to now see when these cancel, aren't we left then with a -1 for that product? And what we end up with is our 0. So since 0 is the very next angle, don't draw a straight line. So this didn't go directly in between here. If we really wanted to kind of use some angles in here, we could have. So don't necessarily draw a straight line, but it goes to that point, the origin, pretty directly. Okay, don't go a straight line, but it goes pretty quickly to that. But we still have a few angles to go in the second quadrant. We now want to go ahead and do 3 pi over 4. Sure you can see this. So throw in a 3 pi over 4. We know that's root 2 over 2. But in the second quadrant, it's a negative root 2 over 2. So when these guys cancel, we get that negative root 2, which is a negative 1.4. Add that to the 1, we ultimately get an R value of a negative 0.4. So remember what that means. We're going to be looking at the 3 pi over 4 angle. So we're looking up here. So here's 3 pi over 4. So on this line is our direction, but we're going to go backwards a half step. So that actually means we are right about here. That's our next little point here. All right, real quick, we're going to skip the pi over 6 angle because that gives us the ugly root 3 over 2. So the next angle that finishes off the second quadrant would be pi. So do pi real quick and see what we come up with. Plot that point, connect it. And pi should be the nicest. No fractions or anything to worry about. All right, do we get a negative number here? Another negative r, right? It's a little nicer number. We get a -1, correct? So that means we're looking out here at pi. So we're looking in this direction, but we take a step backwards so that we end up right here. So if we now connect this to this, that is the entire third quadrant or second quadrant. We went through all of these angles. So what has just happened in the third quadrant, we now need to reflect into the fourth quadrant. So if I now do a simple little reflection of this should reflect over here, kind of like this, right? So if you look at the black and the red are a reflection around the x-axis. And then this one should do a reflection here to where that goes pretty directly to this point that was right here that we had gotten, so that it still looks like a cardioid. But the reason this is probably our most common type of a question is, see this little loop in here? This thing now has kind of this inner loop that we created because we start getting all of these negative r values. Okay. So a really common question in terms, and you'll see some of them here in a second, and definitely tomorrow, what we do, and the idea of that little loop on the inside. Okay. All right, last one real quick. This one for us to set up our table, do this, you got to do a little bit of algebra first. So solve that for r. So r would, we're not do that there though. So r is just 2 divided by cosine of theta. All right, so throw 0 in. Cosine of 0 is 1. So I would have 2 divided by 1. So looking out at angle 0, we go out 2 steps. We're going to skip the pi over 6 because that's the weird √3/2. So jump to pi over 4. So this would be the cosine of pi over 4 is √2/2. So that's really 2 times 2 divided by √2. So 4 over a √2. I have to cheat for that. Oh, I don't have that one. So when we do that, that should give us 2.8 as an estimate. So look at pi over 4. So here's the pi over 4 angle. Go out to 2.8-ish. So probably right around here. Let's do one more. Do pi over 3. See what you get. Plot that new point. And see if we understand what's happening. Yeah, mine will look pretty good, I think. All right, what do we get for that value? Good, should get 4. All right, it should have been a half, so we should get 4. So now if we go out to pi over 3, and we go out to that fourth circle, that would be our third point. What is this starting to look like? Yeah, straight line, specifically a vertical line, right? Doesn't that look like those are all lining up vertically? So if you remember, the very last day or two before winter break, remember our conversions? Do we remember what our cosine of theta was equivalent to? X. So what this really is x equals 2. Isn't that what we're forming right now? Aren't we forming a vertical line going through 2? All right, so not a coincidence. There'd be some discontinuities. Like if I did one more, if I go to pi over 2, you're going to have a problem. It would be undefined. But it's just lining up just like it should because our cosine of theta is x equals 2. Okay, that's what we were kind of talking about when we left before break. All right, good, Mo. Should throw you a cookie. They brought me all these cookies for bath, and the last thing I need is some cookies right now after winter spring break.
I appreciate the gesture.
Maybe you can just take all of them. You know, when you can distribute them. I can't distribute them right now. I've been in trouble for shared food. All right, so that's graphing those. If you then go to the back page, the derivative of these guys. It's lovely. You're going to see right down here. Very lovely. But the derivative of a polar equation. So recall what we just mentioned from last set of notes before break, that r cosine of theta is equal to x. And then if you remember that, then hopefully it's not too much to remember that r sine of theta is equal to your y. If I ask you to take the derivative of this equation by itself, we could say that this is the derivative of x with respect to theta, because it's in terms of theta. That's our independent variable. And then dy would be the derivative of y with respect to theta. So it's similar to our parametrics. If I want dy over dx, then if you look at these two ratios, couldn't we take the dy d theta, whatever that is, divide it by the dx d theta? And when I do that, so that's what I'm doing right here, dy d theta, dx d theta, doesn't that then let the d thetas cancel each other out, and then we get the dy over the dx? Okay? We can then do this, right? All of this is taking the derivative of, if I want dy d theta, think about this as the product rule. So if I ask you to take the derivative of that, we would do the derivative of the first term, leave the second, plus leave the first term alone, and then the derivative of the sine of theta would be cosine of theta. So that is where this comes from. It's nothing more than the product rule for that conversion that we dealt with before break. All right. If I ask you to take the derivative of x, we would say this is dx d theta, pretend like that's an x, and it's a product rule here, r prime, leave cosine alone, plus initially leave the r alone, then the derivative of cosine would be a negative sign, so we'll change this to a minus. R sine of theta, that is where this comes from. So it's really up to you. I honestly have never memorized this formula, even after having done this for many years. What I just know is that if I want the derivative of y, I'm just doing the derivative of r sine of theta, that's its conversion, and then I'm going to do the derivative of x, and then that's going to produce this formula every single time. All right, to me, it's a little easier to keep that down. We already would have this stuff down up here anyway. Okay. So if we go to this problem, let's see how this would then play out. If I want you to take the derivative of this, so now be very careful. There is a difference between dy dx and r primed. So don't think you're just going to do r primed equals and then do -2 sine of 2 theta. They mean two completely different things. R primed is telling us the rate of change of r. Is r getting longer or shorter? It doesn't give us the slope of the curve at a point. Okay. So if we want to now do this, for us to find dy dx, we've got to do dy d theta and divide it by dx d theta. So again, all we are doing, I mean, you can just copy it right here, but all this is us taking the derivative of the conversion for y, that r sine of theta is equivalent to y. Do the product rule with that, that will give you this numerator. All right, so we're just going to write that r prime sine of theta plus r cosine of theta. And then one giant fraction bar. Same thing in our denominator. Here is what x is equivalent to. X is an r cosine of theta. So if we just do our product rule, take the derivative of that, it would produce the r prime cosine theta minus the r sine of theta. What's going on up here? And then we want to evaluate that. We'll do it at 0. We'll probably just do one of these. A lot of times we'll do a bunch of them, but we're kind of hoping to save some time that way. So before we can now do this, so if I want my slope, dy dx, I actually need r primed. R primed is nothing more than the derivative of r, just like it would have been all year. So if I asked you for the derivative of r, you would have said that that would have been a negative sine of 2 theta, and then times 2. So that's r primed. Then we have sine of theta, so we just rewrite that, plus r cosine of theta. R is the original problem. So I'm now going to substitute in r as a cosine of 2 theta, and then times that other cosine of theta. We'll clear where all this is coming from. All right. We go to the bottom. R primed is once again the derivative of the original problem, so negative 2 sine of 2 theta times the cosine. Then you're going to do minus r. R is the original problem, cosine of 2 theta. And then times that sine of theta. And as you can see, this is not for the faint of heart. There's a lot of stuff going on there. If I wanted to be really, really mean, I would give you pi over 6 or pi over 4 or pi over 3, because you now have to evaluate all of these. But you can see typically, to keep this manageable, these are nice values to evaluate. So this is not going to be as rough as maybe it would seem to appear. I'm going to take that negative 2, let your theta be a 0. So if I come to this expression right here, isn't the sine of 0, 0? So then that's a negative 2 times a 0. I get another sine of 0. So that's the first part of the numerator. We just have a negative 2 times 0 times 0. Plus, the next one, you're going to do cosine of 0, so that should be a 1. And then you get another cosine of 0, which is a 1. Go to your denominator. I'm going to have that negative 2. The sine of 0 is 0. Cosine of 0 is 1. Minus, this would become a cosine of 0, so 1. And then the sine of 0 is 0. So that mess turns into a simple 1 in the numerator. And then we would get what? A 0 in our, do we all get 0 on that? I would show you this here. Yeah. So this slope is undefined. We've already talked about it a little bit at the beginning of class. If we were to graph this guy, all of these on the front page here, don't all of these have places where we have vertical tangent lines? Yeah, we have a bunch of them here, bunch of them here. So that's just a place where we would have been vertical. And that's what would be causing this derivative to be undefined, right? Now, if you're really bored, since I do have them, we're not going to go through them all, so I'd like to try and get another one done. At pi over 2, it's really just a matter of evaluating a unit circle. We would have gotten 0. And at pi, you would have gotten a slope of undefined again. Right? All right, so let's try to get one more done. So go to number 2. A little space here. Since we know we're going to need r prime, let's do that first. Honestly, that's normally what I do anyway. I'm a little rusty, since that was the first one we've done in a while. Just find your derivative right away. So let's just say negative 3 cosine of theta. That's r prime. Then if I want dy dx, it's just this formula here if you want to get it memorized. If not, just take the derivative of the conversion for x and y. But right now, for the sake of time, I'm just going to rewrite that formula. So that's going to be r primed, which is a negative 3 cosine of theta, times the sine of theta. Then we have our plus r, which is the original function, times cosine of theta. Your denominator is r primed times cosine. So right here, r primed times cosine. So r primed is the negative 3 cosine of theta again. And then times the extra cosine theta. Minus, please use parentheses here. You're going to be doing minus r, so I'm writing this now, minus r. R is now a binomial. So just to make sure that we remember to distribute, set up a parentheses. That's our r. And then times sine of theta. And then in this case, we're just going to do it at pi over 2. Can we see all that up? Yeah, close enough. We're probably finishing with this one. Evaluate all those now, because whatever this evaluates to be should be our answer. So go through that, see if we can get this. We won't have time for the last one. We'll do that tomorrow. See if you have it set up correctly first, and then see what we come up with. This you should actually get a number. You should get a numerical value out of this if you do it correctly. All right, anybody brave think they know what number we get here? No, or Lily, with 2 L's or 3. Good. Should get a 0. If you go all the way through that correctly, that should end up giving you a 0. And again, I'd give you these 90s or 180-degree angles, 0, pi over 2 pi to make this nice, so that we can evaluate these nicely. But yeah, this should have ended up being a 0. The cosine of pi over 2 should have been a 0. The sine of pi over 2 is a 1, but this all just cancels because of the 0. Careful with this now. 3, so you initially would have 2 minus, and then the sine of pi over 2 is a 1. So that's going to give you a negative 1, but the cosine of 0 is 0. So that's why our numerator ends up being the 0. Down here, cosine of 0, or sorry, cosine of pi over 2 is 0, 0, so that's all going to go away. But then down here, I get 2 minus 0, because the sine of 0 is 0 times the 3. And then this is a 1. Wait, sine of pi over 2, sorry, let me change that. This is minus 3. So we get what? Negative 0 over 1, ultimately. And then 0 over 1 should give you your 0. We also have a lot of places where the slope is 0, right, on these. You know, like I pointed out at the beginning, slope is 0 here, slope is 0 here, slope is 0 here. A lot of places for zeros and undefineds. All right. All right, we kind of got done. Bring this tomorrow. You definitely want to see this last question. So we'll finish that tomorrow, and then we'll move along to the next set. Okay? All right. You guys at home, go. We'll see ya. Stop this.